In this video, we look at the concept of Voronoi diagrams. To motivate this concept, let's look at the following problem, which is called the nearest neighbor problem. We have endpoints P1 up to Pn, and we'd like to store this in a data structure such that given a query point Q, we'd like to find the closest point among these endpoints to point Q. So we could motivate this problem as the post office problem. Imagine you have n post offices, and the location of the ith post office is the point Pi. And we'd like to store them in a data structure such that given a point in the map or on the map, we'd like to find the closest post office, which would be the closest point. To see how they connect to Voronoi diagrams, let's consider two related questions. For this point Pi, we could ask which region this point Pi services. In other words, for which region the point Pi is the closest point. If we have 2 points only, then these two questions are easy to answer. If you draw the bisector of these 2 points, P1 and P2, any point that is below this red line will be closer to P1 than it is to P2. And the other way around if you have a point above this red line. So in other words, if these are the only 2 post offices, every point below this line will be closer to P1, and therefore P1 will be serving all these points in this region of the plane. So for instance, for this point Q, of course, point P1 is the closer point, so Q lies in the region of point P1. In general, a Voronoi diagram is basically given by this concept. So you have endpoints, and we'd like to decompose the plane into some regions R1 up to Rn, such that for every point inside the region Ri, point Pi is the closest point to the point Q. So for instance, the region of this point is this light gray area. So any point inside this light gray area is closer to this point than it is to any other point in the input point set. Before seeing how to compute this Voronoi diagram, we have to understand some discrete geometry properties of a Voronoi diagram of a set of points. In particular, the first thing we'd like to understand is to prove that the cell of Voronoi diagram of P are convex. So, or actually it should be the cells. The Voronoi regions are also called cells. Some cells are unbounded, for instance this cell is unbounded, whereas some cells could be bounded. But either way, they're all going to be convex shapes. Why is this true? Because look at one point P, and we'd like to figure out what the cell of this point P is. Similar to what we saw previously, by drawing the bisector of all the points, by bisecting all those line segments that are connected to P, we can find the cell of this point P. So for any other point, connect the point Pj to Pi, and draw the bisector. So this will be another one bisector. So this bisector has 2 halves. The half that is closer to this black point, and the half that is closer to the red point. So the half that is closer to the black point is going to be a half plane, which is a convex shape. And so for every point in the input, we can do this procedure. So we get n bisector or n-1 bisectors, and thus n-1 half plane. We look at the intersection of all these half planes. That would give us some region that is going to be convex, because a half plane is a convex object, and we know that the intersection of 2 convex objects is convex. So therefore, the intersection of all the n-1 convex objects will also be convex. We claim that this cell of point Pi is exactly equivalent to the intersection of all these bisectors. This is relatively easy to see because any point inside this cell is, by definition, is inside all these half spaces. So therefore, it is closer to point Pi than any other point. And similarly, for any point that is outside this cell, we know that at least one bisector contains this point P on their red side. So therefore, that point is going to be closer to some other point than the black one. So far we have proved that the cells of a Voronoi diagram are convex. The next thing we'd like to prove is that unless all the points of the P lie on a line, then the Voronoi diagram is essentially made up of a straight line segments, or rays that go to infinity on one side. To prove this, first observe that the cells from the previous lemma that we know that all the cells are convex objects. Of course, the finite cells are polygons or convex polygons, and the infinite shapes are basically something like this. Okay? To prove this, observe that we only need to prove that we cannot have a full line L in our Voronoi diagram. Because so far what we have proven is that the Voronoi diagram is made of a straight line or line segments or rays because of the convexity of the regions. But it could be that we could have one cell that has one full line as part of it. If you have a full line, then it follows that the Voronoi diagram is separated in two parts. This means that there can be no bisector intersecting this full line L. Because if there is a bisector that intersects line L, then we'll have a Voronoi vertex on this line L. So we'll be decomposing this line L into rays. So since there are no bisector intersecting L, this follows that all the bisectors should be parallel to L, which means all the points should be on one line. The next thing we would like to prove is that the size of the Voronoi diagram is linear in the plane. So what do we mean by size? The size is essentially the total number of vertices and edges of a Voronoi diagram. Assume that M is the number of edges and I is the number of vertices of the Voronoi diagram. And H is the size of the convex hull of all the points. We like to use Euler's formula that says in a planar graph, the number of vertices minus the number of edges plus the number of regions equals 2. We can almost apply this Euler's lemma or formula, but the problem is that this is not technically a planar graph, because in a planar graph you can only have normal edges, so you cannot have these infinite edges. There are two ways to fix this. One is mentioned in the book, and then in that method you just connect all these infinite edges to some random point outside. But another way to do it, which is I guess more intuitive, is to just put a bounding box. So I'm just going to do the bounding box method. It's a bit more, ends up being slightly more complex in math, but it's a very straightforward idea that we have seen before, i.e. the putting of the one bounding box. So therefore I'm going to use it here as well. So place a bounding box around all the input points. The number of region is n plus 1 because we have one region for every input point, and we also have an infinite region that is outside the bounding box. All the vertices have degree 3, so we clip these edge here. So now this will be a vertex of the planar graph, this will be another vertex, and this will be an edge of a planar graph. And as you can see, all the vertices have degree 3 except these 4 corner vertices. So therefore we can write the following. So the number of edges, 2 times number of edges is equal to sum of the degrees. So what is the sum of the degrees? We have V vertices in this planar graph. All except 4 have degree 3. So this is the total sum of degrees of everything that has degree 3. And 4 vertices have degree 2. This is the total sum of the degrees in this planar graph. And we know that this should be equal to 2 times the number of edges. And finally, we know that the total number of edges is equal 4 plus the size of the convex hull plus the original number of edges in the Voronoi diagram. Why is this true? Well, we had 4 initial edges added by the bounding box. Every infinite ray intersects the bounding box 1, so therefore creates 1 extra edge, and the number of rays is equal to the size of the convex hull. I'm not going to prove this, but it's easy to prove. And finally, we had m normal edges in the original Voronoi diagram. So if adding them all up, we get the total number of edges in this planar graph. And by the same logic, the number of vertices is equal to 4 corners plus the number of rays, which is equal to size of the convex hull plus the original number of vertices in the graph. So having all these equalities, the rest is basically just math. So these are the equalities that I have. Euler's formula, I replaced r with n plus 1. And this was what I had from before, which simplifies to 3v minus 4. And then I also had these two. How do we do math here? Well, first I double this equation. So that will give me this equation. And from here, I could replace 2 times e as 3 times v minus 4. If I simplify things, I get v equals 2 times n plus 2. And then by replacing v with this, I get that the number of original intersection points is this much. However, notice that the size of the convex hull is at least 3. So this means this is at least 2 times n minus 5. To get to the number of edges in the original Voronoi diagram, we start with here, here, which is this formula. And then this is by replacing v as from here, we get that e equals this, and then this simplifies to m equals this value, and since h is at least 3, then we know the number of edges is at least 3 times n minus 6.